So one interesting thing that we're going to see about these radical reactions is that they all operate by the same mechanism, where the first step is going to be making the radical. The second step, which we call the second step, but it really happens many, 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 many times, is that radical making more radicals. And then finally, radicals combining in what we call termination. And so we're going to start with the first step, initiation. Like I said, this is the mechanism for all radical reactions, not just this reaction. So they always start with initiation, which is where a molecule with a covalent bond spontaneously forms two radicals. And usually this requires the input of energy, like heat or light, and generally only happens for relatively weak bonds. So here the mechanism is going to be starting with chlorine or bromine, and then splitting that 2-electron bond, giving 1 electron to each chlorine. And so in doing this, you're creating two radicals where we didn't have radicals before, and setting off what we call the radical chain. The second step of this mechanism is propagation, where radicals create more radicals. And this step happens repeatedly. In typical reactions, except for polymer reactions, we only show it once. But it's happening many times. So let's say our chlorine is in a solution of cyclohexane, where all our hydrogens are the same. It's going to encounter a CH bond, and it's going to not want to be a radical anymore. So it's going to take this hydrogen so that it doesn't have to be. So we're going to make a new bond here, using 1 electron from the chlorine radical and 1 electron from this single bond. The other electron is going to go to the carbon. And in doing so, we're going to create HCl. We're also going to create a new radical. And this is where, if we're bromine instead of chlorine, we're going to want to make sure we make the most stable radical. So the weakest CH bond is going to form the most stable radical. We'll also create HCl as a side product. Now, that's going to want to find something else to react with. And so what it's going to react with is going to be chlorine. So only a few, in this initiation step, only a few of our chlorine molecules actually became radicals. This didn't happen at all like 100%. Remember, we said radicals are relatively rare in solution. So most of the chlorine, even after initiation, is in this covalent form, where you don't have any radicals around. Same process is going to occur, where we're going to break this bond to fix this radical. And what we're going to get as a result is going to be our product, and then some additional chlorine radicals, which now can repeat this process. Then, eventually, some of our radicals will, instead of finding an alkane, maybe find each other. And so this termination step can have a few different forms. One can be that 2 chlorines find each other and form chlorine again, chlorine radicals. One can be a chlorine radical finds a cyclohexane radical. And one can be that 2 cyclohexane radicals find each other. And because the radicals are not there in a very high amount, all of these will be very minor products. Well, especially the third one. The other 2, you won't notice that they came from termination because they're exactly like other molecules in solution. And so for all of these, the mechanism is just taking those 2 single electrons, putting them together to create a new covalent bond. One interesting thing is seeing something like this might tell you that maybe this is a radical reaction, and might want you, if you think that your reaction might be a radical reaction, there are experiments you can do to try to figure that out. And so this as a side product could be interesting from trying to figure out what your mechanism is. So if we look at these 3 major steps, this initiation step is always thermodynamically uphill. It requires energy because you're breaking a bond and you're making something that's less stable. You need light or heat to do that. The last step is always going to be favorable because you're taking these reactive radicals and getting rid of them. I want to focus in on the energy of this second step because that's going to be important to why chlorine and bromine react differently. So if we look at this propagation in terms of the reaction energy, we can see that both steps are exothermic. When you go from this chlorine radical in ethane to the ethane radical in HCl, that new HCl bond being formed is stronger than the CH bond that broke. So this is exothermic. In the second step, this is also going to be exothermic because this new carbon-chlorine bond that we see here is stronger than the chlorine-chlorine bond that we broke. So both steps here are exothermic, as is the process overall. The rate-limiting step is going to be the one with the highest transition state. So that's going to be this first step. And that's the step that we're going to focus on when we're dealing with why chlorine and bromine react differently. So if we think about this first step, I don't know if you remember from 331 the Hammond postulate. What the Hammond postulate says is that the transition state resembles the species that's it's closer to in energy. So for an exothermic reaction like this, the one I have highlighted, the transition step will resemble the starting material more than the product. Now with bromination, that first step is not exothermic. So the formation of HBr does not make up for the loss of the CH bond. And so because of that, in bromination, it has the same rate determining step or rate limiting step, but that rate limiting step is now going to be endothermic. And because it's endothermic, it's not going to resemble the transition state is not going to resemble the starting material, but it will instead resemble the product, which it's closer to in energy. So this is a very simple alkane, but let's see how this would be impacted if we now have a more complicated alkane. So if we zoom in on this first step, we'll see that the transition states look pretty different. So in this first example with the chlorination, because it's exothermic, the transition states will resemble the starting material. And the starting material is not different whether you're going to the primary radical or the secondary radical. So we see very little difference in energy for the transition states. The two products have different energies, but the ratio of the products is coming from the energy of the transition states. In our second case with bromination, this is an endothermic reaction, so this transition state is closer to the products, so it resembles the products. So this transition state is going to have some character of a secondary radical, which is going to make it lower in energy than this transition state, which will have the character of a primary radical, which is less stable. So in this case, we see a difference of energy in the transition states. This will lead to selectivity in forming the product, where we will primarily form the most stable radical, the one with the weakest bond, the one with the more stable transition state. So the take-home message here is, because of all of this, for bromination, you generally get a single product. It's a very selective reaction. Whereas for chlorination, you tend to get a mixture of products. So it's not a particularly useful reaction. In reality, the halogenation of alkanes is not a widely used synthetic reaction because we can easily buy the products. The allylic bromination that we'll see in a future video is going to be much more useful, but you can use these reactions to really start with very simple compounds and start doing synthesis to get to more complex products. So you could imagine coming from something like this and using the synthetic tools that you learned in 331 and 332 to get you more complicated products. So here, this is a 331 review question where we're going to use the radical reaction we just learned in synthesis to get this specific product. So in this case, what we want to think about is, well, we know that there's only one way to functionalize an alkane. We want to functionalize it at a very specific position. This hydrogen here is attached to the tertiary carbon, so we want to use bromination to replace that with a bromine. So that's the only way we can functionalize an alkane, so we don't need retrosynthesis to tell us that's something we need to do. But now we need to think about how to get from this tertiary alkyl bromide to this tertiary alcohol. We cannot do it via direct SN2 reaction. That will not give us the desired product. Because if we do a reaction like this, instead of getting SN2, we'll get an E2 reaction. And that'll give us something like this. That's not a problem in this case because we can use this to get to our final product. So our final product will want to do an acid catalyzed hydration. So with water and acid, we can take that alkane, take it to the alcohol. And so this is going to be, there's going to be a lot of good problems in chapter 13 that allow you to review your synthesis skills from the first half of organic chemistry.